So I'm going to talk about, again, some of these crazy things. Maybe a key thing to think about is that, Malcolm was just talking about problems that are on the order of, something like 14 orders of magnitude in terms of the challenges that will have to be overcome. That, again, very reasonably sounds problematic. But I'd like to make the argument that actually this is sort of the default regime that we like to work in, where we are many, many orders of magnitude from what we actually want to measure. Because I'm talking a little bit about some of the work that we've been doing, somewhat less applied and more looking at fundamental physics using zero and ultra-low-field NMR. I think the title that I had in place on the website was measuring zero at zero field. I was just recently back home in Portland, so I was inspired to go with the new subtitle of keeping ZULF NMR weird. So we'll talk a little bit about that today. Some of the questions that are still out there, in addition to the more immediate practical things of importance, figuring out how to, say, make a vaccine for a given virus, figuring out how to solve problems related to cancer, seeing out how to actually image these sorts of things to determine whether or not a tumor is a problem or not a problem. There's a lot of these really big questions that are, perhaps in some ways less important, but certainly deeper. The questions of what is the universe, what is matter, how are the ways that things can actually interact? And that's some of the stuff that we also are looking at and that we found that ZULF NMR can actually also contribute to. So for example, the question of what is the dark matter the universe made of? There's more of it than there is of normal matter. So it's probably worth knowing what the majority of all the stuff is. We've had a lot of success with the standard model of particle physics. The table's almost filled up ever since they measured the Higgs boson, but there's still some questions going in there that suggest that there's more to be found. And the question that I'll address a little bit more today is the question of whether the weak nuclear force has any actual impact on chemistry. That's a little bit of a teaser, and we'll get into that later. But first of all, unfortunately, Alex was not able to join us today, so we're going to miss out on the actual history lesson. I am, of course, not Alex. I lacked the cigar. However, it being a little after 5 p.m., I did make myself a cocktail, and hopefully, at James's suggestion, the rest of you took the brief break in Danila's talk to also find yourself a drink. I guess if you're in the U.S., maybe a little bit less appropriate, but it's an NMR conference, so do as you will. So the usual historical introduction that I like to talk about is basically shown in this picture here. So the at least most likely apocryphal story of the history of ZULF NMR is that once upon a time in Alex's lab, there was a student working on, I believe this was called the beta magnet in Berkeley. And at some point, this magnet was quenched. And allegedly, Alex's story was that, the student came into his office, told him that you'd quench the magnet. Alex said, well, I guess your new project is zero field NMR. And then as the story goes, he thought about it and decided it was actually a good idea and began to investigate this. We have no evidence of whether this is actually true. We do know that based on what we have from the picture, based on the length of the jean shorts and the height of the socks, this was probably sometime in the 80s. That's really all that we know about that.
John,
we can go a little bit further back into history.
Can I interrupt? We have evidence because that student is Tony Bileski, and he told me that himself.
Okay, all right, very good. I was never sure exactly who this photo was of, so I need to write this down somewhere, but I don't have a pen next to me. So I'll try to remember that it was Tony Bileski. Okay, so now we're going to reach a little bit further back into history. Yeah, again, we don't have Alex with us today, but to some extent, Alex would probably at least give the impression that any history that happened before Alex was involved in the particular problem of zero field NMR doesn't terribly count. But I will point out, a few notable early things. Of course, in 45, 46, we had the discovery of nuclear magnetic resonance. And then in 1954, there's a paper that is actually remarkably hard to find, though the reference is easy to find in a lot of places, where Packard and Berrien used proton-free precession at Earth's field. This then led to other applications of actually using Earth's field NMR as basically a proton magnetometer to study basically geomagnetic effects. And again, more and more things have happened since then. But again, it's long before I was born, so I wasn't around to read most of the papers. I've read some of them, but at the last minute, it was hard to find all the other references. So then we come back to the 80s, where Alex became involved in NMR. I guess I should say, before there, also nuclear quadrupole resonance, NQR, and ferromagnetic resonance were around, which can also be referred to as zero field NMR. And I think given some of the definitions that we've been using, where what we just say is that ultra low field NMR is what we define as the case where the Zeeman interaction is much, much smaller than the effective local interactions. In that case, we could still have NQR and ferromagnetic resonance all within this big tent of ZULF NMR.
John, can I quickly, there's a wide audience here. Can you quickly explain what NQR stands for and very briefly summarize what you mean by that?
I thought I said that. Nuclear quadrupole resonance. In these cases where you have a quadrupolar nucleus, because you have such strong couplings, especially in solids, between electric field gradients and nuclear quadrupoles, you end up already with energy level splittings around the order of megahertz. So without having any additional field for polarization, you actually get some level of nuclear spin polarization just due to those quadrupolar interactions. And so as a result, you can actually do these experiments without any magnetic field applied, just by driving transitions with RF irradiation. So hopefully that's at least a basic idea. So again, we come to the 80s, and the technique that was used there was basically field shuttling, not quite as elegant as what's going on in Novosibirsk now, but essentially the same idea. You prepare your initial state at high magnetic field. You have the advantage that you have all of the NMR tools for control of nuclear spins. You can apply all the RF you want, all the pulses, to prepare for whatever state it is that you want. Then you rapidly shuttle your sample down into a zero field regime, depending on how strong your local interactions are. This was mostly solid state NMR. So you didn't have to be that careful about getting to, close to exactly zero. But I think they still it had some shielding to make it below zero or below Earth's field. Then you either suddenly turn off the magnetic field or adiabatically take it down to zero and apply some series of pulses. Then you turn a field back on, bring your sample back up to the magnet and measure it. This had to be done inherently as an indirect experiment, similar to what has been shown by Kostya, where you're basically taking each time point in that zero field evolution, point by point, by measuring what's actually being shuttled back up into the high field magnet. And really part of the motivation for this was that, of course, especially in solids, you have generally some degree of anisotropy. Actually, by definition, you have anisotropy in your sample. And this gives rise to effective broadening, because all you're really seeing is the projection of whatever interactions are present inside of that principal axis of any given crystallite projected onto that main magnetic field of the spectrometer. So of course, if you have a crystal, then depending on whatever angle you have, you get different relatively sharp peaks that correspond to the projection of that dipole-dipole coupling tensor onto the high field vector, or pseudo vector technically. But when you have a whole bunch of different crystallites, this gets kind of smeared out and you end up with these powder patterns that anyone who does solid state NMR knows and perhaps loves. The advantage of zero field in this case is that you no longer have to worry about this different symmetry, this different high field vector that you are projecting things onto. So as a result, everything is effectively the equivalent of a single crystal spectrum in terms of the line width. And so that's what was shown in some of the main motivation behind what Dan Weidekamp and other people in the Pines lab were working on in those days. Again, you can see other cases where at high field, let's see if I can adjust my pointer here for a second. So here over at high field on the left is what happens when you put this molecule into a high field NMR magnet without any spinning. Just a big shapeless blob. But if you actually do these zero field cycling experiments, you can actually start to, again, get some level of resolution coming back out. You can go further and further. You can start doing high field, zero field correlation spectroscopy. So you've got the big broad thing at high field. Everything is nice and narrow at zero field. You can also look at quadrupolar interactions, so on and so forth, et cetera, et cetera. A little bit later in the 80s and the early 90s, there was also a lot of pull sequence development going on. One that's really interesting, especially in the context of some of the nitrogen vacancy work going on. So in 1987 is the first reference that I could find referring to this pull sequence that is the zero field equivalent of the high field CPMG experiment. So it's a pi on X, pi on Y, pi on X, pi on Y, repeated a number of times. So again, this is the basic building block of the X, Y, N pull sequences. This was then developed further by Antoine Lohr. A couple of really fantastic and incredibly complicated papers that were published in 1991, looking at all of the different possible symmetry predicted pull sequences that can be done at zero field NMR, with zero field NMR. And again, one of the simplest ones to produce effectively a zero field echo is really identical to what would now be called, at least by the NV community, the XY16 pull sequence. All kinds of great work going on. I really encourage people to try to read this paper. I think to this day, understand maybe 25% of it. I think the two people that definitely understand it are Antoine Lohr, still understands it. We've confirmed that. And Tobias Yolander, who was really working closely with him for a while after he came to visit in Berkeley. But unfortunately, Tobias went off to go have a real job at Intel. So if somebody else can go take on and understand what's going on here, everybody should win. Later on, in efforts to actually do direct detection, Alex reached out over to the physics department, talked to John Clark, who was working with these superconducting quantum interference devices, or SQUIDs. And in the early 2000s, they were actually able to make measurements in basically the regime that we would refer to as ZULF. Certainly Ultralow-Field in this case, where they looked at, for example, if you just look at phosphoric acid, you get just a single peak at the proton resonance. Then again, you bring in your protons, so they're actually coupled to trimethylphosphate. You see a nice J coupling. Again, here the Zeeman interaction is much, much larger than J, so it's still on that edge of the ultralow field regime. And again, here's a little picture of what's going on. Basically, you have to do this whole thing in liquid helium. You have further liquid nitrogen jackets to prevent too much boil off. Definitely possible, but it's challenging. Again, people who do normal NMR are used to doing helium fills, but are perhaps less accustomed to the extra effort required to actually build cryogenic equipment, especially when you can't just go buy it at the store. These days, you can actually go buy exceptionally sensitive squids commercially, but you still have to build the rest of the instrument yourself, which is not terribly easy, I can tell you. And using these squids, again, one of the favorite figures that I've seen from these days is measuring magnetic resonance image of a bell pepper that was placed inside of a can of Coca-Cola. This is the kind of application that just seems like utter nonsense to anybody who has not ever done high field NMR and thought about the issues. But of course, if you have done high field NMR, you know that if you were to wrap your sample in metal, you're going to see nothing other than possibly the NMR facility manager coming to scream at you because clearly you're an idiot and you're probably in the process of arcing all kinds of awful things between the probe and your sample. I don't recommend doing this at high field. Maybe modern equipment is foolproof enough that you won't damage anything. But even then, you really wouldn't see anything because of the skin depth of that metal means that RF cannot penetrate. However, if you go to low enough frequencies, it's no problem. As we continue on,
I just want to give you a quick, you have about 20 minutes-ish, 20 plus 5, let's say.
Yeah. Excellent. I'm just coming to the end of the history. So yeah, 2009, as Dima had mentioned, at some point, Alex then got into communication with the Butker group to see whether they could actually make NMR measurements using atomic magnetometers. And so Micah did so. And here we see measurements of the two different isotopomers of ethanol, which continued to look the exact same way as they did back then. Then, of course, in 2010, I went to grad school, so at that point is when I defined the end of history and the invention of the modern era. And so then we have the question of, so why would we actually do ZULF NMR? Apparently I have animations. So on the one side, we do have practical advantages in terms of portability. At the moment, the most portable instruments are probably still larger than the most portable high field NMR measurements. So I agree with Malcolm entirely that we have to be careful about saying what exactly the advantages of zero field NMR are. Again, one could argue that the possible miniaturization of NMR, of high field NMR, cannot go that much further. Of course, there's a lot of great work being done by a lot of electrical engineers. For example, Jens Saunders, who I believe is currently in Stuttgart, has done really excellent work with miniaturization of just about everything from the coil to the spectrometer and so on, and even then, small permanent magnets so that you could in principle get close to that range of a cell phone sized device. Maybe with the NVs and diamond, things can get even smaller. And if you get to throw out that magnet, you get an even further reduction in the size of the instrument. But that's not necessarily a fundamental advantage. In practice, it's nice that you don't have to deal with the magnet, but as you've seen in some of the other talks, sometimes we still do field shuttling, in which case, well, we still have some magnet anyway. But the really more fundamental advantages are the fact that when there's no more magnetic field, all of our frequencies tend to be rather low. So as a result, if we have a conductive sample, we can actually see through that. It's no longer a problem. Furthermore, susceptibility is no longer an issue. In high field NMR, if you have heterogeneous magnetic susceptibility, and then you put it into a big magnetic field, you end up having different magnetic fields induced throughout the sample. This leads to significant broadening. If you're at zero field, 0 times whatever susceptibility is still gives you 0, and it's nice and convenient. And then, maybe at an even deeper level of it really being truly fundamental is that the symmetry of the problem is just different. High field NMR, you have a preferred axis at all times, and that is just a part of the instrument. And I think actually Malcolm put it really nicely in the introduction of his book Spin Dynamics by saying that NMR is sort of a unique spectroscopy where the largest interaction is actually between the sample and the spectrometer, rather than just some small perturbation on top of just what's actually happening in that molecule on its own. At zero field, we're back into that more conventional spectroscopy regime where we're just perturbing the molecule in its more natural state. Put another way, you can think of high field NMR as using an altitude measurement to measure somebody standing on top of a mountain. Most of what you're measuring is the height of the mountain. So that's basically your Larmor frequency, which is, it's very nice. It tells you how big your magnet is. And if you've, gone and acquired a 1.2 gigahertz magnet, it's always comfortable to be reminded that your expensive purchase was actually worthwhile, that it still is at 1.2 gigahertz, plus or minus a little bit. And on top of that, you have the chemical shift. If we are talking about, something like carbon-13, the chemical shift range compared to your Larmor frequency is again about the height of your average human, including children, I guess, even if it's 1 to 2 meters. So yeah, you can do that. And what's impressive is that you're able to do that with conventional instrumentation. And then if you wanted to see the equivalent of your spin-spin couplings, now we're talking about like the thickness of a human hair. So if you really wanted to, you can actually do this. And in fact, that's what is done in modern high field, high resolution NMR. But again, this seems remarkably complicated. And through real feats of engineering, it actually is possible. But one could argue that really you're better off actually looking at things without all of this extra information thrown in there. So, ZULF NMR is kind of the equivalent of, if you wanted to look at that human hair, just look directly at the human hair. You don't need all this additional information. Except, of course, in this metaphor, your altitude meter is incredibly sensitive compared to a microscope, but yeah, so it goes. Of course, the other advantage is that now it's actually easy. So, we've shown that you can use these commercial magnetometers. I think the time from when we started doing this until we had collected most of the data was on the order of about a week. But then because I was involved, the time between having the data and publishing the paper took about 1.5 years. James can comment further on that if he wishes. And it's, yeah, and again, it's relatively portable. So here's a picture of our earlier design of a portable ZULF NMR spectrometer. You can see that it's outdoors. If we had power, it would actually operate there. You see a lot of pictures of high field NMR magnets outdoors, but they're not operating. And then we have our more recent design where it's all on one 19-inch rack. It's similar to what Danilo is showing, except for the one key development that we've added here, which is the presence of a bottle opener on the side of the instrument, which is notably missing from other instruments, but we found to be extremely valuable. There's additional space here. Really, we just chose the height of this rack so that it would be convenient to work with while standing. It could be smaller, or again, maybe we could find a way to fit a small refrigerator in there so that we actually have a source of beer and a way of accessing it. Also, you can do stuff with dark matter. I already talked about that recently, so you can look at the perm talk if you want to. but sort of inspired by that, we were trying to find a way that we can get the highest possible polarization in a repeatable way. So we built this, high pressure, metal bomb that we were planning to pressurize up to 50 bar, so we can just have Sabre running continuously. However, our HPLC pump turns out is borrowed and doesn't actually work at. It can't actually generate a pressure difference anymore, although it is able to keep on cycling things at a constant pressure. So we can't have our sample made out of glass anymore. It has to be made out of metal. So we had built a metal NMR tube. And so in the meantime, we figured, hey, let's do some measurements inside of this metal tube. It's made out of titanium, so it's non-magnetic. At one point, it did have some stainless steel in it, which made everything impossible, but we just cut that off and replaced it with PEEK. And we were able to show that you can actually do some basic reaction monitoring while flowing in parahydrogen. And I think there's actually a poster about this that Dudari is going to be presenting today. So I'm not going to go into it any more detail other than saying that we are able to look through metal, which is not terribly surprising.
John, can I quickly ask you to, you raise an important point there where you say, like, we can see through the titanium tube, no problem, but this tiny amount of steel inside it just screwed everything up entirely. Can you comment on why that is? And like very briefly, why?
So stainless steel in principle is non-magnetic, but as soon as you touch it, especially if you machine it, it becomes magnetic. In principle, you could actually degauss it the same way that you used to degauss a cathode ray tube TV or monitor. Basically, just by applying an oscillating field that drives it through this BH hysteresis curve until it comes back down to zero. That can be done in principle. We didn't have that set up at the time, so we were not able to actually degauss the little bit of steel. But in principle, it should be possible to measure through other materials, provided that you're able to get them to stop being magnetic.
And Scott Seltzer asks whether Johnson noise from the metal is a concern.
I was definitely concerned with it, but it turned out to not be a problem whatsoever. So, again, hi, Scott. But yeah, I had been concerned about this before, but actually it turns out that it's not really a very big addition. And also this magnetic shield didn't have a ferrite inner shield. So the magnetic noise floor was already around 10 femtotesla per root hertz. Using the Q-spin magnetometer, had us at around 15 femtotesla per root hertz. So it seems that the addition from the conductivity of titanium didn't really seem to be much of a problem at all.
Thanks. And you have just under 10 minutes left.
Yep, I'll get to the real part of the talk soon. And so we started thinking about the real further possibilities. We can look at all the possible, say, two-spin coupling tensor symmetries. You can then visualize them with this spin drops package from Stefan Glaser. Then you see you can have something that's isotropic, like your singlet, like a singlet, or like a scalar coupling. You can have vector-like couplings, and you can have your rank 2 couplings, similar to, for example, the dipole-dipole coupling. Then if you look at which of these are effectively invisible to high field NMR, you see that actually most of them don't show up in high field NMR spectroscopy at all. Or I should say in the coherently in the spectrum. They do show up in terms of relaxation, but you don't actually see the direct spectral signature of them. And in fact, these are the most colorful ones, so it's disappointing that we don't get to see the rainbow patterned coupling interactions. Some of the more interesting ones are actually these rank 1 interactions that are by necessity antisymmetric couplings. So in principle, you can actually have these in the form of a antisymmetric J coupling. And what's interesting is that they're actually directly tied to chirality. So if we're assuming a parity conserving mechanism for how this interaction shows up, then what we find is that we actually end up with a pseudo-scalar Hamiltonian, which means that upon reflection, it changes sign, and in all other ways, behaves just as it should as an energy and as a scalar. But the fact that it changes sign upon inversion means that if you would take say a right-handed molecule and then replace it with a left-handed molecule, you'll actually see a different sign for that interaction. And so some work that we were doing with Tobias and with Jonathan back at Berkeley, we were showing that by looking at this coupling term with zero field NMR, in principle, you could actually have a direct measure of the chirality of a molecule, where you're not interacting that molecule with right or left-handed circularly polarized light, but actually you can almost think of it as interfering the spatial chirality of the molecule with the chirality of the Hamiltonian, which, if nothing else, is really cute. But now I was just saying that, okay, so we're talking about, we have this parity conserving form. So in that case, you have a pseudo-scalar Hamiltonian, and necessarily it's only possible for that to exist in the case of a chiral molecule. The reason for that is actually a little bit tricky. It took me a while to understand it properly, but I think it's actually pretty straightforward. We know that that Hamiltonian has to be, for any molecule, has to be symmetric under any of the symmetry operations that describe, for example, the point group of that molecule. So if it's antisymmetric, we know that it is not. So if it's a pseudo-scalar, and if the point group of your molecule contains any improper symmetry operations, including reflections, then it's not possible that the pseudo-scalar is going to actually be there, because it's going to change sign. Therefore, it is not allowed to be there if you have an achiral point group. So it's also, I guess, a chirality sensor in a way. But in principle, you could also have a parity non-conserving origin of these nuclear spin interactions, which necessarily, because electromagnetism cannot generate a parity violating effect on its own, has to involve actually the weak nuclear force. So what we'd effectively be looking for in this case would actually be a direct measure in molecules of these weak force effects, which has never been done before. So again, this weak nuclear force does not conserve parity, maximally violates parity. And so in this case, you end up with this Hamiltonian becoming a scalar again. So now it's possible that you actually have this in an achiral molecule. And in fact, the presence of an antisymmetric spin coupling in an achiral molecule is direct evidence of this weak force effect. If anybody's curious, there's a little bit of math below. I'm not going to go into that. But the important thing is that, so if you have a heavy molecule, a heavy nucleus like thallium, you get into the sort of millihertz range of interaction strength. But if you had something that's light in both cases, like hydrogen and fluorine, you'd expect something that's more in the microhertz range. I also need to take a moment to talk about the difference between orientation and alignment. In the English language, we tend to use them interchangeably. And regrettably, also in chemistry and in the NMR community, we tend to also use orientation and alignment as meaning the same thing. But a key important difference is that orientation is different from alignment. Something that's, for example, okay, the table that many of us are sitting in front of, or a desk, is an oriented surface. You can tell the difference between up and down. again, COVID, so maybe you're more familiar with hiding underneath the desk, but above and below are in fact different places. For an aligned surface, it wouldn't make any difference. So you can think of like a z-axis where you don't care about positive or negative as being alignment, but the positive ray going up is oriented. This is important because of this is important because of the different ways that these coupling tensors actually transform. So, the dipole-dipole coupling, as people are familiar, for example, if you're looking at residual dipolar couplings, is going to transform with this order parameter that has this P2 cos theta term. A rank 1 coupling term is going to transform more like your p orbital rather than a d orbital, and so is just the expectation value of that cosine theta, where theta is the angle between some chosen lab axis and the various molecular axes. Then furthermore, you can go look at actually how these behave in the presence of an electric field. So if you have dipolar molecules, then you see that basically the dipole moment times the local electric field divided by kT is what you have for rank 1 terms. If it's rank 2, you have to square that and then divide by 30 instead of just by 3. So for smaller electric fields, you can actually have relatively fast scaling of antisymmetric terms rather than terms like the dipole-dipole coupling. So what you can do is basically take your sample that's filled with dipolar molecules that have some sort of dipole moment and place it between high voltage electrodes so you can actually orient your sample. And so the first thing this does, taking the example of a magical version of HF, where it doesn't have any of the actual bulk properties of HF, such as auto-ionization and hydrogen transfer. First you'll see a dipole-dipole coupling show up, but then if you actually modulate that field, you see that you actually end up modulating the dipole-dipole coupling at a different rate than you modulate this this antisymmetric J coupling. And actually, by modulating at the right frequency, you can make it possible to observe effects, even if it's a very, very small antisymmetric J coupling. If you think about what happens if you just have 2 nuclear spins, initially in say, IX minus SX, so they're pointing in opposite directions, then they just beat back and forth, as we were shown by, I think, probably both Thomas and Michael on the first day. So we know how that behaves, and then along other axes, you see no projection whatsoever to within how well you've aligned things. Now, if you put in just this small antisymmetric term, you'll see that they will try to, rather than just beating back and forth, they'll try to actually rotate slightly. However, whenever they invert, they'll start rotating back the opposite way. So you'll get a very, very incredibly small effect along the transverse axis, like on the order of an attotesla. That is not generally measurable. This is also assuming prepolarization in a 20 Tesla magnet. So even then, you're still looking at an incredibly small magnetic field. But if you modulate this electric field at basically the J coupling, you actually get things to build up. So it starts to go a little bit, then it inverts, it goes a little bit the opposite direction with respect to the overall projections of this IX minus SX term. But that starts to build up more and more, and we actually get into a regime where we're looking at a decent fraction of a femtotesla. So again, we talk a lot about something like a 10 femtotesla per Reuters noise floor. This is 20 times smaller than that, but we can handle 20 times smaller. Again, 14 orders of magnitude is hard to deal with. Factor of 20 is easy. We can just average 400 times, and then you're there. When you also include that dipole-dipole coupling, things get more complicated, and now there's 3 things, so we go beyond what I'm able to actually explain as an experimentalist properly. But in addition to this sort of wiggle, you get the spins going kind of like this. You actually end up with a slight enhancement that is hard to exactly explain why it's being enhanced. Interplay between double quantum terms as well, and you end up with this sort of in the few femtotesla per root hertz regime, which is very measurable. We're actually working towards making these experiments real. Kirill and Lyubov have been doing a lot of design work and have actually gotten the parts made. I just saw these yesterday, and the initial stuff has been assembled by Kirill. And basically it's just a pair of electrodes encased in PEEK that can handle the high voltages with enough space for the sample in there in between. And of course, additional work is being done on the high voltage electronics, but this is newer, so I thought we'd show that. In principle, it may also be possible to do this with something like thallium fluoride, which is a nasty enough molecule, but furthermore also is not available as a convenient dipolar liquid, but you can get access to it in molecular beam experiments, such as are being done as part of the Centrex experiment to look for charge parity violation in thallium. But because they're actually using thallium fluoride already for that experiment, in principle, it could actually be very possible to conduct a similar experiment using a thallium fluoride molecular beam. So we've been investigating also how it might be possible to make that work, basically by turning off the field they would usually use and just the electric field. Yep. So again, in summary, ZULF NMR, as you've heard from before, has a lot of practical applications. But for those of you who like the more exotic interactions, don't worry. ZULF NMR also offers a wealth of weird, exotic NMR for the enthusiasts. I'd like to thank everybody who was involved in this. A large range of people have been involved in different aspects of the ZULF project. And of course, in particular from the original part of it, Alex's involvement has always been crucial, and of course, as well as Dima's, and really, and Micah Ledbetter also probably deserves, if Alex and Dima get to be the fathers of NMR, Micah is at least the fun uncle. I guess I get to qualify as the weird cousin. So thank you all, and if there's questions, I can try to answer them.
We have about 2 minutes for questions, then we're going to go to the post session, so I will just cut this off in a couple of minutes. But well, Malcolm asked whether HF at C60 could be useful, and Malcolm has his hand raised, so maybe he wants to unmute and comment.
Yeah, thanks, John. Yeah, HF C60. No, I mean, yeah. Well, Dima, I think, has answered saying it would be the effects would be too small. But what I wanted to ask as well, actually, is
okay. Dima only likes heavy nuclei, but actually, in that paper, we considered HF at C60, and really the issue is concentration. Is that the effective dilution is a bigger hit than other possibilities. I think more practical would probably be something like if we're talking about fluoromethane or trifluoromethane, that 20 bar or something condenses. So we're thinking that something like that might be a more practical, slightly more practical.
I would have thought that if you're always about 14 orders of magnitude too low, then a few more orders of magnitude don't make any difference anyway.
Well, anyway. so in this case, we're only like 2 orders of magnitude away.
Okay.
So so using HF at C60, I think would put us 5 orders of magnitude away. So on like 2 orders of magnitude, we can handle by just averaging for a week, which is exciting, actually.
Can I ask something else? Is that okay?
Go ahead.
I'll allow it.
If you don't have suppose you have a molecule with an inversion center, so it's not chiral.
Yeah.
But if you could measure the difference between the if they have 2 parts of the molecule which are related by an inversion center, then actually I don't know how this parity thing works. But would the
I think I know where you're
J
going
coupling,
with this.
Yeah, okay. So what I'm thinking of is measuring the difference between two antisymmetric J couplings related by an inversion center.
So the problem is that in order to be able to actually observe it, you have to have a non-zero projection of the antisymmetric J coupling tensor onto the electric dipole moment. So that means that D dot J1 has to be there. And for the same reasons as before, it is forbidden for that term to exist and be non-zero in an achiral molecule.
Okay, yeah, I get it. Yeah, there's no electric dipole moment, basically. So you're, in the example I gave, so you're in trouble. Yeah, okay.
Yes. So like there are cases where you can say that in a molecule that you could have an antisymmetric coupling, but it wouldn't project onto the dipole moment, so it wouldn't be measurable.